Today, we're grabbing a wrench and completely smashing one of the most stubborn myths in the entire automotive world. This whole idea that just bolting on a massive, thicker radiator is the automatic, magical cure for an overheating engine. In this explainer, we're diving deep into the actual thermodynamics of engine cooling. I'm going to train you to think like a master technician. That means relying on proper diagnostics, flow rates, and actual physics, rather than just throwing expensive aluminum at a problem and hoping it goes away.
Here's our syllabus for today's run-through. We've got 6 parts: the physics and the myth, shop triage and diagnostics, anatomy of the core, the supporting cast, doing the shop math, and finally, fluids, testing, and final checks. Let's get right into it.
Section 1. The physics and the myth.
Okay, before we even think about turning a wrench, we have to understand the fundamental physics happening under the hood. This chart right here completely reframes what a car engine actually is. You see, an internal combustion engine is basically just a massive, incredibly powerful heater that, just happens to make a little forward motion on the side. Only about 30% of the energy from fuel combustion actually turns into motion. The other 70%, that is pure waste heat. So your cooling system is carrying a massive, continuous thermodynamic burden right out of the gate.
So, keeping that massive heat burden in mind, let me ask you a question. If more heat needs to be rejected, why do massive, thick, 4-row radiators often actually perform worse than modern dual-row setups? Seriously, a lot of guys out there think bolting on a giant, super thick core solves absolutely everything. But, well, thermodynamics has a totally different story to tell. And this sets up a totally, absolutely crucial concept you need to master.
The concept is delta T, and it brilliantly illustrates why thicker definitely isn't always better. Delta T is simply the temperature difference between your hot coolant and the ambient air outside. The core formula for heat rejection is Q equals U times A times delta T. Now think about this. When you stack 4 rows of tubes together, the air passing through the 3rd and 4th rows at the back has already been heated up by the front rows. So your delta T drops off a cliff. Plus, a core that thick essentially acts like a brick wall in front of your engine, severely restricting the airflow you desperately need. You just hit a wall of diminishing returns.
All right, moving on to Section 2, Shop Triage and Diagnostics.
We're shifting gears from theory to real-world shop triage. Your job as a pro is isolating the root cause before you ever let a customer blow their cash on parts they don't need. Do not just order a bigger radiator right away. Walk through this exact diagnostic funnel every single time. First, check the coolant level and condition. Second, test the thermostat. Look, if it's stuck closed, even a radiator the size of a billboard isn't going to help you. Third, verify the water pump is creating proper flow velocity. Fourth, inspect the fan and shrouds. And finally, you got a pressure test to ensure you don't have an internal leak, like a blown head gasket pushing combustion gas directly into the system.
Check out how these specific symptoms break down the root cause. If the car runs perfectly fine on the highway but starts boiling over in stop-and-go city traffic, you are almost certainly looking at an airflow issue, maybe a failing fan clutch or just a bunch of dead bugs blocking the fins. But if it's overheating constantly, totally regardless of your speed, you might be dealing with a flow rate issue, like a worn-out water pump impeller. Remember, proper fluid velocity dictates your heat transfer. If the coolant isn't moving fast enough, your radiator is basically just a very expensive paperweight.
Now here's a very specific, scary symptom you'll see when an engine is running right at its absolute maximum thermal safety margin. Let's say a customer says their heater suddenly starts blowing cold air during hard acceleration or when they're towing a trailer. Listen, that is not a broken heater core. The vehicle's ECU is actually in triage mode. It's deliberately cutting coolant flow to the cabin so it can concentrate every last drop of available cooling on saving the engine block. That is a massive red flag that the vehicle's thermal limit has been breached.
Let's dive into Section 3, Anatomy of the Core.
Time to get our hands dirty and look at the hardware. When you're sizing up an upgrade, materials absolutely matter. Interestingly enough, traditional copper and brass actually have a much higher raw thermal conductivity than aluminum does. But there's a catch. Copper is heavy, and it requires thicker tubes just to be structurally sound, which totally offsets that thermal advantage. Modern full aluminum cores are way lighter, they let you use wider, thinner tubes, and they feature incredibly strong brazed joints from the tank to the core. And that is exactly why aluminum has become the modern standard for high-performance tank radiators.
But hey, material is just your starting line. To really maximize heat rejection, you need some seriously smart geometry. High fins per inch, or FPI, drastically increases your surface area. Louvered fin designs actually slice right through the boundary layer of air, keeping a warm film from blanketing the metal.
Flat and oval tubes increase the coolant contact area, and adjusting the tube pitch, the spacing between the tubes, optimizes your airflow. Throw in some turbulating inserts inside the tubes to intentionally disrupt laminar flow, and you will dramatically boost the total system heat transfer efficiency.
Section 4. The supporting cast.
The crucial takeaway here is that your radiator does not work alone. A massive high-tech core is totally useless without its supporting partners doing their jobs perfectly in tandem. Think about how air naturally moves. A bare fan without a shroud only pulls air straight through the exact circle of its blades. That leaves the entire outer corners of the radiator doing absolutely nothing. A proper fan shroud funnels all that air, forcing the fan to pull through every single square inch of the core. Adding a proper shroud can increase cooling effectiveness by a staggering 30 to 50%. An oversized radiator without matching properly shrouded airflow is quite literally just dead weight.
In fact, if you just slap a massive radiator into a car without balancing the entire system, like if you just leave the stock thermostat in there, you seriously risk overcooling the engine. Yeah, overcooling is a thing. The symptoms of over-upgrading include super slow engine warm-up, terrible fuel efficiency, and the ECU constantly dumping excess fuel because it's tricked into thinking the engine is still cold. Your coolant flow volume has to perfectly match the engine's design so it can reach and actually maintain its most efficient operating temperature.
Up next, Section 5, doing the shop math. Grab your notepad for this part, rookie. If you're building a high-output engine or prepping a car for the track, you cannot guess on radiator sizing. You've got to do the math. Here's the golden shop rule for thermal management. An engine generates roughly 42 BTUs per hour of waste heat for every single horsepower it produces. So, if a customer rolls in with a stock 150 horsepower engine that they just turbocharged up to 300 horsepower, they have literally doubled their heat output. The stock radiator was absolutely never designed to handle that kind of thermal load.
So here is exactly how you calculate that required thermal margin. Step 1. Multiply the vehicle's horsepower by 42 to get your total BTUs. Step 2. Grab a tape measure and find out the physical frontal area you actually have available in the grill. Step 3. Use the baseline that a high-quality aluminum core rejects about 4,000 BTUs per 100 square inches. If the math tells you your new high-horsepower build needs 600 square inches of frontal area to survive, you've got to find a way to make it fit, while also matching up the correct airflow and hose fittings.
Finally, Section 6, fluids, testing, and final checks.
We are in the home stretch now. You've diagnosed the system, you ran the math, and you bolted in the correct parts. Now we have to talk about fluid chemistry and safety pressure testing. Look at the reality of fluid dynamics here. Pure distilled water is absolutely the best fluid on Earth for transferring heat. It wildly outperforms a standard 50-50 antifreeze mix when we're just talking raw cooling capability. The trade-off, obviously, is that pure water gives you zero freeze protection and a lower boiling point. So you have to tailor your coolant mixing ratio to the specific environment the vehicle lives in. But remember, improper mixing, or using regular tap water that leaves scale buildup, will instantly destroy all the performance benefits of that brand new radiator. Even if you've got the absolute perfect fluid mix, your biggest hidden enemy is air. Air is just a terrible heat conductor. If you don't properly bleed the cooling system after a repair, those trapped air pockets are going to act like thermal insulators inside the system. They severely disrupt your fluid flow velocity, and they create these deadly localized hotspots right inside the engine block. Those hotspots can actually crack a cylinder head before the temperature gauge on the dashboard even twitches.
And that leads us to the final sign-off. Never, ever hand the keys back to a customer without safely pressure testing the system. Here's the routine. 1 minute in, do a solid visual check of your hose routings and make absolutely sure there are no external blockages like debris or bent fins choking off the front of the radiator. At 5 minutes, hook up your pressure tester and pump it exactly to the radiator cap's rated PSI. Then, you wait 15 minutes. If that needle drops even a single millimeter, you've either got an external fluid leak somewhere, or worse, a hidden internal leak like a blown head gasket. Find it, fix it.
Let's wrap up today's session with this quote. Cooling is a balanced system, not a single part. A bigger radiator cannot fix a broken system. That right there is the master technician mindset. Thermostats, flow velocity, airflow, shrouds, and surface area, they all have to be working in perfect mechanical harmony.
So I'll leave you with this final thought. The next time you see a temperature gauge spike while you're driving under a heavy load, are you just going to run to the internet and buy the thickest, meanest-looking 4-row aluminum core you can find? Or will you actually step back and diagnose the system? Take these skills back to your shop, trust the physics we talked about today, and fix it right the first time.